So then I have a list with gene sets. Yeah, and you see that their name has been cleaned. There's no hallmark here anymore. So I have a list of gene sets, and on the other hand, I have a matrix with my bulk RNA-seq data. So now I can do the actual analysis. And this analysis will take some time. So while he is running, I can explain how it works, and for that I will go through the tutorial that you can download on the e-learning system. So what is rROMA doing? Well, it is making a PCA plot of my bulk RNA-seq data. This is basically the PCA plot that he's making. So every point that you see here represents a gene. And the original axis, you don't see them here, but the original axis would be the samples. So it's not the same PCA plot as you make when you analyze your data with DE-seq2 or with HR. In that case, you'll also make a PCA plot. But in that PCA plot, you will plot the samples. The points will be the samples, and you will check if you see outlier samples and if the samples can be separated according to the group that they belong to. So this is not the same. It's kind of the inverse thing here. The points are the genes, and the axis, the original axis, are the samples. So, and in this space, in our case, it will be an 8-dimensional space because we have 8 samples, and every sample will make one axis in this space. So in this space, the points are plotted according to their expression levels. So each gene has an expression level in each of the 8 samples. These expression levels are used as coordinates in this plot. So as you can see, the points are colored here. So the colors represent different gene sets, different pathways. Yeah, we have a green pathway, we have a red pathway, we have a yellow pathway, and we have a blue pathway. So for each gene set, he will find the first principal component. So that is always the direction in this 8-dimensional space that shows the highest spread between the points, between the genes of that particular pathway. So the red line that you see here is the first principal component for the red points, the red genes, the genes that belong to the red pathway. It shows the direction that gives the most spread between the red points. And this is true. You go from here to here. That's the most spread that you can draw between these points. And he will calculate the first principal component for each gene set in your bulk RNA-seq dataset. So the green line is the principal component for the green points, and the blue line is the first principal component for the points, the genes from the blue pathway. And then he will try to find pathways, gene sets, for which there is a very high spread along this first principal component. You see here for the genes of the red pathway that this is the case. There is a very high spread. You go from here to here. That's very highly spread out. So he's going to calculate this spread for every gene set, and he's going to compare the spread that he finds here for the red gene set to the spread that he finds for random gene sets. So basically what he will do is he will project all the points onto the red line. He will calculate the spread for the red points on the red line, and then he will take a random gene set. So he will take a point here, a yellow point here, a blue here, a red one, a green one, another yellow one, and here another yellow one. He will project these onto the red line and calculate the spread of these random gene sets. And he will compare them. And if the spread of the red genes is much higher than the spread of the random gene sets, he will say, hey, this is an interesting gene set. And he will call that gene set over-dispersed. It has a higher dispersion, a higher variability, a higher spread than you would expect based on random gene sets. So that's one thing that he will look at. But he will also look at another phenomenon. So as you can see, all these first principle components, they all go through the same point here. And this is the center of the original distribution of genes in this 8-dimensional space. So every principal component that he calculates needs to go through that point. So this is the center of your gene distribution. And he will also look for gene sets for which all or most of the genes are located at one side of this center. And the green gene set is a very good example of this. So all the green genes lie at the right of the center. There is no green gene that is located here. So the spread of these green points is not so high. It will not pop up as an over-dispersed gene set, but all the green genes are located at one side of the center. And this is also important. So he tries to find these gene sets. And these gene sets are called shifted. They are shifted compared to the center of the distribution here. The blue gene set is another example of a shifted gene set, you see. All of these genes are located here at one side of the center of the distribution. So basically, he does the two things. So he finds over-dispersed gene sets by calculating the spread and comparing the spread to that of random gene sets. And here for the shifted gene sets, he's going to calculate the median expression of that gene set. If a gene set is nicely centered here around the center of the distribution, then the median will be 0 or very close to 0. That's the origin of your 8-dimensional space. However, if a gene set is shifted, it means that the median will not be close to the center of the distribution. So the median will be far away from 0. So what does that mean now, shifted and over-dispersed? Well, shifted is the easiest to explain. So a shifted gene set means that all the genes in that gene set will be up or down-regulated. An over-dispersed gene set is also interesting. It contains a mix of up and down-regulated genes. But also these pathways are interesting to find because you can have pathways with positive and negative regulation. In the meantime, he has finished the analysis. So we asked him to generate an output here, and you see that this output is a list with 13 objects. There's a lot of information here. What we need is the object called module matrix. So this one. What does it contain? Well, for every gene set, these are all gene sets, for every gene set, it contains a number of measures that he has calculated. So what are the important measures here? Well, L1 is an important measure. L1 is the amount of variance or spread or dispersion that is measured along the first principal component. So the spread along the first principal component. So the thing that he uses to find over-dispersed gene sets. The higher L1, the more over-dispersed the gene set is. He calculates a p-value for the L1. This p-value is the result of the comparison of the dispersion that he calculated for that particular gene set compared to the dispersion of random gene sets. So the lower the p-value, the more different this dispersion is from the dispersion of random gene sets. So the more likely it is that this gene set is over-dispersed. Another important measure here is this one, the median expression. It's the median expression of all the genes in the gene set. So again, after projecting them on principal component number 1. So if you project them to the red line, all of them will have a coordinate on this red line, and then you're going to search for the median of these coordinates. For this gene set, the median will be close to the center because it's not shifted, it's over-dispersed. You have down and up regulated genes. For the green gene set, however, the median expression will be somewhere here, will be very far away from the center, from 0. The higher or the more negative, also possible, so the more positive or the more negative the median expression, the more shifted this gene set is. And also for the median expression, he calculates a p-value by comparing the median expression of a particular gene set to the median expression of random gene sets. So here also, the lower the p-value, the more likely it is that this median expression that you calculated is very different from the median expression of random gene sets. And random gene sets, of course, you assume that they will all be centered around 0, so that their median expression will be close to 0. Maybe one more thing that I have to mention here, apart from the p-values, you also have q-values, both for the dispersion and for the median expression. What's the difference between the p-values and the q-values? Well, the p-values are p-values that have been corrected using a Bonferroni correction. So you have to do a multiple testing correction here because you're going to do this test for every gene set in your list of gene sets. So we're going to do this comparison 50 times. So if you do multiple tests on the same data set, you have to do a multiple testing correction. So here, the p-values were generated by doing a multiple testing correction using the Bonferroni method. So we multiply them by 50. The q-values are p-values that are obtained by using a false discovery rate-based multiple testing correction method. So typically, the Bonferroni is much more stringent than the false discovery rate-based method. So if you have a limited number of gene sets, you typically look at the p-values. If you have a high number of gene sets, you are going to look at the q-values. So 50 is not so big, so we are going to focus on the p-values.